So before the break, I was staring at the blackboard and at the audience and at the director, being puzzled about what to do next. And it turned out that it's actually very simple. So we had this formula that the reflection on H in SL2C was realized by this conjugation with U equal to the standard X minus the standard Y. Now what I failed to recognize is that this E is really the exponential map of the Lie algebra SL2C. And conjugation in the Lie algebra SL2C is the same as the adjoint representation. The adjoint representation for the general linear group is just conjugation, right? So that means that this can be written as the add of x of pi over 2u applied to h. But now we have this wonderful formula that the conjugation by add can be realized as the exponent of the infinitesimal conjugation of add of u. And this is the formula I wanted to have. So the problem was that I didn't recognize this expression in front of the blackboard, which is pretty hopeless for a Lie theorist. But maybe not so hopeless for a Lie theorist with lack of sleep. Okay, let's continue. Okay, I think I should say one more thing about root systems. And this is, so we have this E, and we have this R satisfying the properties of a root system. In particular, we have that R is finite, consists of non-zero elements, and we have that R spans E. Now if alpha is a root, then the claim was that there existed a reflection in alpha, a reflection S alpha, reflection in alpha, with the property that the roots are preserved. And of course in the context of Lie algebras, what I did is I used the Killing form to construct this reflection, to define this reflection. But in the statement of what it means to have an abstract root system, I avoided on purpose mentioning the existence of an inner product, because it turns out that it is not necessary to use an inner product to define what a root system is. On the other hand, there is a natural inner product around, or there are natural inner products around, and this is what I now first want to discuss. First thing that I want to prove is that if there exists such a reflection, then actually it is unique. So this implies that there exists a unique reflection with that property. Now let's give a proof of this. Now the idea is that we are going to look at a group K. K is going to be elements of GLE, so invertible linear maps from E to itself, with the property that R is preserved. Okay? Now R is a spanning set. And that means that phi is completely determined by its restriction to R. So R is spanning. And so that means that the map from K to the group of bijections of R, mapping phi to the restriction of phi to R, that this is an injective group homomorphism. Now, R is a finite set, so the group of bijections is finite. Conclusion, K, since this homomorphism is injective, K has to be finite as well. So K is a finite, this group is finite. But we know that a finite group is in particular, it's compact. Well, this is really now we're using the proverbial big cannon to shoot on a fly in Dutch. Not going to do that. It's finite, so that means if I start with an inner product on E, then I can take the average. I can take the pullback of this inner product by elements of K and take the average over K. So then this produces an inner product which is invariant under K. So, or another way of saying this is there is an inner product on E such that with respect to this inner product K becomes a subgroup of the orthogonal group for this inner product. Well, if that is so, then in particular elements S alpha with this property are elements of K. So that means that S alpha, so in particular, the S alpha must be orthogonal with respect to that inner product. But before the break I said that the reflection in an element is unique if we require this reflection to be orthogonal with respect to a given inner product. So this makes that the reflection is really unique, right? This group is independent of any reflection. So this produces an inner product. Now, any reflection that I find here must be in the orthogonal group for that inner product. And therefore, there can only be one such reflection. And so this proves uniqueness. We are done. Now, let's look at the group generated. The group generated by the S alphas. So this is going to be a subgroup of GLE. And in fact, since the generators preserve the roots, all elements of this group preserve the roots. So this is a finite subgroup of K, or it's a subgroup of K. K is finite, so this group is a finite group generated by reflections. It's a so-called finite reflection group, and in this particular context it's called the Weyl group. Of the root system R. And this Weyl group plays an important role in getting some more properties of the structure of Lie algebras. Okay. I now want to turn to the classification of root systems, and first I need some more properties of roots. The first property I'm going to prove is, so maybe I should say one more thing. So now given a root system, given abstract root system, E, R, there is no inner product specified. Nevertheless, we know that there is a unique group of reflections around, generated by reflections around, a finite Weyl group. And now what one can always do is choose an inner product which is Weyl group invariant. And then the formula for a reflection becomes lambda minus 2 lambda alpha over alpha alpha times alpha. And then one of the properties of a root system asserts that this will always be an integer. So in the classification of root systems, there always will be an inner product around, and what we can do is we can speak about once we have an inner product, we can speak about angles between roots. Now there is a question.
Okay, so that's an integer if lambda is a root as well, isn't it?
You are perfectly right. The question is, this is an integer if lambda is a root as well. So this is true for all beta in roots. Yeah, absolutely. Thank you.
But the expression
itself is, of course, the defining expression for a reflection. So this is this expression is true for any lambda, and this coefficient is an integer if lambda is a root. Yep. Okay. Thank you for making the remark. Okay. Now, these numbers, I'll denote this number here by n alpha beta. So this is the so-called Cartan number. And what I now want to study is the possible values of the Cartan numbers. And this has something to do with angles between alpha and beta. So in this context, now that I have this inner product, how could I define an angle between alpha and beta? Well, basically by the following formula. Angle that the inner product of alpha and beta is given by the well-known cosine rule. Well, by the Cauchy-Schwarz inequality for the inner product, the length of this inner product is at most equal to this product of lengths. But that means that I can express this inner product as the product of length times a constant, and this constant belongs to the interval -1, 1. That means that the constant admits a unique expression as the cosine of an angle, where the angle is chosen from the interval 0, pi. And that angle is really, by definition, the angle between the roots alpha and beta. Of course, if I try to classify things, then I start, say, with an orthonormal basis of E. So I start in some R, well, let's just start with a finite dimensional vector space and an inner product, and then I'm going to try to construct root systems where the Weyl group should act where the reflection should be orthogonal with respect to the given inner product. And that means that the angles between roots will become very restricted, as we will see in a moment. That's the idea. Okay. So the angle is defined in this way. Now, so that means that the expression, so n alpha beta, is equal to inner product beta alpha 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 2 times, and this can be rewritten as alpha beta cosine angle over length alpha squared 2 times. So that means if I take the product of n alpha beta with n beta alpha, then, of course, I mean, the length of alpha drops out if I replace this by a 1. And then if I take the product of these, then the rules of alpha and the rules of alpha and beta are interchanged, meaning that this quotient drops out. This gives a 4, and then the angle doesn't change because it's really a non-oriented angle. And so that means that I get the square of the cosine. But these are integers. And that means that this has to be an integer.
You will also have some, or are you assuming that the length of alpha and beta is 1? Wouldn't you have something like...
Yeah. The length of alpha and beta drop out because of the change of rules. So if I take this multiplication, so I end up with an integer, and at the same time it should be 4 times cosine squared of phi alpha beta. Now, of course, this is between 0 and 1. So that means that this product only has 4 possibilities, or 5 possibilities. 0, 1, 2, 3, 4. Now this means that phi alpha beta, that the cosine squared is 1, so this is either 0 or pi, which means precisely that alpha and beta, alpha is plus or minus beta, and this is the case of proportional roots. So if I assume that the roots are not proportional, then these are the only possibilities. And what I'm now going to analyze is what this means for the n alpha beta and the n beta alpha. You see, these are integers as well. And their products are 1, 2, and 3. There aren't that many possibilities to get 2 as a product of integers. Same thing for 3. Right? So we get the following table of possibilities. Assume that alpha and beta are not proportional, and I also want to avoid some double counting, so I'm going to assume that the length of beta is at least the length of alpha. Because otherwise, with every pair alpha beta, I would also get a pair beta alpha, and this is something that I'm going to avoid now. Now I can make a table. So here, let's put the products of n alpha beta and n beta alpha here. Now, and let's first investigate what happens if we take 0. Well, so we have n alpha, we get n beta, and we get the angle of alpha and beta. So, yeah.
Is there n alpha beta and n beta alpha?
Thank you. Question was whether this was correct, and the answer is no. Thank you. Now, if the product is 0, it means that the cosine has to be 0. The cosine is 0. This means that the angle is pi over 2. So this is the case of perpendicular roots. But if we have perpendicular roots, then this implies that these are 0 as well. And so this finishes the case of product 0. It's just a pair perpendicular roots. Now we might still wonder what can be said about the quotient of the length, and then the answer is nothing. But the answer can be given for the other cases. So let's now consider the case 1. Now what can we say about that case? Well then, so this product is 1. So the cosine squared is 1 over 4, so the cosine is a half. If the cosine is a half, then the angle is pi over cosine, I'm sorry, 1 over 4, cosine is plus or minus a half. So the angle is either pi over 3 or 2 pi over 3. Okay, so now in this case the cosine is a half. The product is 1, and these are but we have this formula for n alpha beta. The cosine is a half, so what we get is a positive integer, and the product has to be 1, so that means that we are in the case of that both elements have to be 1. It could be either 1 and 1 or minus 1 and minus 1, but since the cosine is positive, the negative values are excluded. Okay, now let's look here. Then both elements, by the same reasoning, both elements are minus 1. Okay, let's look at the case. And what is the ratio of the length? Well, if n is 1 and the cosine is, so what was the cosine? 1/2. So that means that the ratio of the length is 1/2 times 2 is 1, is 1. Okay. Now, this reasoning can be continued, and then one gets the following possibilities. Here one gets an angle pi over 4. And then the quotient of the lengths will be 2, or 3 pi over 4, and one will get, if I remember correctly, 2 and 1, and minus 2 and minus 1, and the same reasoning also gives results for 3. Let's continue. So we get 3, 1 minus 3 minus 1 is possible results, and then the angle can be pi over 6 and 5 pi over 6. And we have 3 for the ratio of the length. Is this correct, or is this the ratio squared?
Yes.
Yeah, so it's the square root of 3 and it's the square root of 2. Thank you. Of course this couldn't be seen for 1. Yeah, thank you. But the important thing is, of course, the reasoning here, and you see that the conditions on the root system are really very restricted. I mean, there are only few length ratios possible and only very few roots. Okay. Now we should keep this in mind. We're going to use it in the classification of root systems, but first I need a few other results to arrive at the classification as quickly as possible. is this how I want to improvise? I have to improvise a little bit, I'm afraid. I think that, okay, this shows that I think I would like to use next time to fill in some details, but now I would like to give some kind of final picture. What you see is that there are only very limited possibilities for angles. And for instance, we could look at the situation, so what are the possible root systems if the rank of the root system, which is really the dimension of E, suppose that the dimension is 1. Well, then of course we just have one root system with given by a one-dimensional space and an alpha and a minus alpha, and this is of course the root system of SU2 of SU2. Now suppose now that the dimension is 2. Then you could play around a bit, and in particular playing with the angles and playing with the Weyl group, and then you would observe that there are only very few possibilities. So there would be the possibility of, and basically the possibilities would correspond. So basically the possibilities are given by pictures like this. Picture with an angle, so picture with an angle pi over 2, picture with an angle 2 pi over 3, picture with an angle 3 pi over 4, and picture with an angle 5 pi over 6. And what do I mean by that? Well, these pictures have to be completed. And let me give the completion of these pictures. And next time I'll explain the completion of these pictures by really proving properties of root systems. But for today I'm just giving the possible rank 2 root system. So pi over 2 will correspond to, well, precisely 2 perpendicular roots. So I have an alpha and I have a beta, and they are just perpendicular. That's it. And the root system consists of plus or minus alpha and plus or minus beta and nothing more. This is basically a product of the root system of SU2 with itself, and this is also called the root system A1 times A1. Okay. The next. How am I? So there is R2. There is a root alpha, and there is a root beta, and the length of the roots are the same, and the angle is 2 pi over 3. And now how can I get the other roots? Well, by taking the sum of these two, the vectorial sum, and this gives a positive system. And then we take the minuses of these roots, like this. This comes completely out of the, well, not completely out of the air now. Basically we know for what angles we have to look, and then what the ratios of the length can be, according to the diagram that I constructed over there. And then we see if we're looking for an angle 2 pi over 3, then the ratios of the length has to be 1, and then what we can try is we can try to look if we can take a sum of two roots. Is that a root again? Is that a possibility? Yes, this comes out as a genuine root system, so apparently well, there is a root system like this. Next time I'll say a lot more, and then it will be immediately apparent that starting from these data, this is the only rank 2 root system that you can construct from them. Okay. Now, the next picture. So we start with the root alpha, the shortest one, and then we start with the root beta in such a way that the length of beta squared over the length of alpha squared is 2. So this is the situation arising from beta squared is 2 alpha squared, and the angle is 3 pi over 4. By the way, I should have said that this is the so-called root system A2. Now, general theory will tell us next week that if we start with roots like this and with an angle like this, we can be sure that the sum of these two is a root again. Now it turns out that this angle, together with the ratio of the length, makes that the sum of these two roots, so add alpha to beta, ends precisely here. So this is root beta plus alpha. Now general theory will explain that actually we can do this once more. We can add alpha once more to beta plus alpha, and then we get another root. Beta plus 2 alpha. And now we have a complete positive root system. Now, how do I know that that this chain of roots stops here? Why can't I go on? Well, the idea is that the angle becomes too small here. But this can be encoded in easy algebra, and from that easy algebra you see that actually the length of this string of roots is going to be this 2 plus 1. So this string has length 2 plus 1 is 3, and therefore there is nothing more to try. This is still very mysterious what I'm telling you, because I haven't given you all the details, but I want to give you a feeling of how these root systems can be constructed out of the data. Now this A2, there is also a string of roots, beta and beta plus alpha, and it stops at 1 plus 1. So there is a string of 2. Now the next and final example of a root system, and of course I have to add the negatives of these roots, and this will then give me the complete root system B2. Now there is another system. Let's draw it over here. This is actually the most complicated, so it is a silly idea to try to do it here. Let's do it over here. So now we start with an angle which is pi over 6 from pi. So we start with a root alpha, and we start with a root. Well, this is always somewhat difficult to draw. Root beta, and then the ratio of the two roots is going to be, what was it? 3. And this makes that we get a string of roots by adding alpha one time, then adding alpha another time, we get something here, then adding alpha another time, and then adding alpha a final time. And now we have a string of 1, 2, 3, 4, 5. This cannot be true. So I did something terribly wrong.
Well, the one in the middle shouldn't be there.
No, you are right. And I always forget what is the best way to draw this, but it is like this, and then it is like this, right? So this is a root. This is beta plus alpha. This is beta plus 2 alpha. And then this is beta plus 3 alpha. We are not completely done yet. For instance, if this is a root, then the reflection in certain other roots will be a root. Again, so we also get the 2 of... We also get... What am I doing?
If you're reflecting b plus 2 alpha.
Right. If I take the sum of these two roots, oh right, then I get a root here. I get the root here, which has the same length as this one. Now, one can show that if one draws these lines, one can really a completion of the root system like this. The length of this string is 4, which is 3 plus 1, and then the rest, I'm not going to explain the rest, but I'll do that next time. And then we also get the negative of this one. We get one here. And this is very difficult to do this on the blackboard, I'm discovering. Especially when it is so big and one has multifocal glasses. So this is longer. And then one has another root here. So it's basically what you see is that it's basically 2A2s, right? Of different root lengths, and one is rotated a bit and put on top of the other. This is the root system G2. Okay. Now, so what appears here is that these roots are determined by 2 roots to start from. And they are called the simple roots of the root system. Now I cannot explain now what the simple roots are. But the idea is that if you have a root system, I'll do that next time, if you have a root system, then you can find a positive system. And this gives a system of simple roots. The simple roots are those positive roots that cannot be written as a sum of 2 positive roots. Now, what you can do is you can make a Dinkin diagram as follows. You start with the simple roots as vertices. And then 2 simple roots, alpha and beta, are going to be connected by n alpha beta and beta alpha edges. And then if you have roots of different lengths, then you add an arrow pointing towards the shorter root. So if length of alpha, add arrow pointing to alpha. Now this gives the so-called Dinkin diagram. Now look at the lecture notes. I'm going to say more about it next week. Look at the lecture notes. Look at the final page of the lecture notes before the index. Then what you see is the classification of all possible connected Dynkin diagrams. Theorem: the connected Dynkin diagrams correspond to the simple compact Lie algebras. So giving these connected Dynkin diagrams achieves the complete classification of the compact simple Lie algebras. Next time I'll do more explanation and we'll go over these drawings one more time, and then you will see that actually they are very natural. Let's finish for today.